Okay, so previously we discussed Reynolds transport theorem in the form of mass conservation and linear momentum. Today we're going to talk about angular momentum, and you'll see that it's pretty similar to the stuff we've done so far. Okay, so remember when we figured out the equation for linear momentum, we had that general form of the Reynolds transport theorem and we had that beta value. Well, if we're going to do mass, we choose the beta value to be m, and if we do linear momentum, we choose that beta value to be mv. So for angular momentum, it follows that the beta value is going to be this. Hopefully you'll remember this from general physics. If the form confuses you a little bit, how about we simplify that? So since this m here is a scalar, you could distribute it inside like this, and you'll see this. R cross mv. So mv you should recognize as your linear momentum, and r is what is called a radius arm. We'll talk about that in a bit. Hopefully you remember some about that, but just know that if you have r cross mv, that is angular momentum. So we're going to take this beta value, and we're going to put this beta value into our general form of the Reynolds transport theorem, and that's going to look something like this, which probably looks a little bit scary right now. Try not to freak out too much about the math. It looks pretty similar to what we've seen before. So here you just have this d beta dd term right over here. That we just subbed directly in our angular momentum. And here we have that beta over m. So we just divide through by m, and we have this r cross v, and this r cross v over here. So just like before, where we had linear momentum, where we had this v here and this v here, or when we had mass conservation, when we had this m over m, or just 1 here and 1 here, this time we have r cross v. Okay, so what does that mean for us? Well, let's do a little bit of simplifying assumptions first, as applied to this problem. So here we have this sprinkler, and water's coming out through here, and water's coming out through here. Okay, so we should rethink our strategy for these kinds of problems, because it does change a little bit. So we'll keep some of what we were doing before, and we'll sort of update it. So the first thing you want to do is you want to identify your control volume, then your control surfaces. Once you've done that, you should, well, you have some options there. I guess the best thing to do would be identify, well, okay, choose a reference point. I'll go into that a little bit when we get there. Then you should identify torques in the system. After that, you should use Reynolds transport theorem for angular momentum, or if you need to, you should use the continuity equation here as well. Once you've done that, you should use symmetry arguments if possible. We'll cover that too when we get there. And lastly, you should just list the vectors and solve and simplify. So really, once you've got the setup down, you're done with the problem. So first, we will identify our control volume, and that's just going to be this entire system here. Nothing too different from usual. Okay, control surfaces. So where do the flows exit? Well, one of them exits here, and one of them exits here. Let's call this guy over here 1, and let's call this guy over here 2. All right, so control surfaces, check. Okay, so what about reference points? Why do we need to care about reference points? Okay, we'll put that off even for like 30 more seconds. So let's go back to simplifying this whole mess over here, because you're probably still a little afraid of the math. So on the left-hand side, if you remember when we had linear momentum, we simply used Newton's laws, and we said, oh, well, this is really dmv dt, so that's ma, and that's simply going to be the sum of the external and internal forces on the system. Well, same thing's going to happen for angular momentum. This over here is just going to turn out to be the sum of the torques on our system. Okay, what about the guys over here? Well, we're going to use our classic assumptions that we've been using so far, and that's going to be steady state. So time derivatives go to 0, incompressible flow, so we could pull density out of the integrals, and velocity profile is constant, so we don't have to really worry about integrating too much. We could just pull pretty much everything out and just integrate over dA. So what does that do? Well, it does the same thing as usual. Gets rid of this control volume term that we still haven't used yet. Okay, and then just like in linear momentum, we are going to simplify to this guy here. So it should look pretty similar to the linear momentum equation. We just had the sum of the forces over here, and instead of V, now we have R cross V. Cool. Okay, so let's talk a little bit about what's going on with this equation. So as before with our mass conservation, we had to look at whether or not it was a scalar equation or a vector equation. The mass conservation equation turned out to be a scalar, because when you're dealing with masses, there's no directionality to that. But linear momentum, there we had this velocity term in here. So that turned out to make it a vector equation. So you had vector forces over here, and you had vector terms over here. Well, what about over here? Well, the dot product will give you a scalar. Rho is a scalar, so a scalar times a scalar is still a scalar. But what happens over here with the cross product? If you remember, the cross product of two vectors will give you a third vector, and that third vector is going to be orthogonal to the other two. So what that means is if you have two vectors, say like these guys, one of them points like this, and one of them points like this, the third guy, the cross product, will be orthogonal to them. So where is that guy going to point? Well, it's going to point out or into the plane of whatever you're looking at. So it's going to point in the third direction. Okay, so this cross product here will give you something in the third dimension. And since we're doing a lot of these 2D problems, what that torque really means is that you're having rotation such as this. But that rotation is really a vector along the z-axis with a magnitude. We just most often represent it like this. And if you remember, your force vectors are sliding vectors, so that means you could move them along their line of action and preserve the system. But your torques are free vectors, which means I can move this rotation wherever I want, and it's going to preserve the system. For that reason, I'm going to drop the vector notation when we're discussing torques. So when we have a torque over here, know that in reality it is a vector, but I'm going to treat it essentially as a scalar, because everything is going to be pointing in the z direction, and we're not going to really have to worry about that. If you're doing some three-dimensional, like real three-dimensional Reynolds transport theorem problems, then you'll have to worry about the vectors and all that stuff. But for us, we're going to basically be simplifying these systems to two-dimensional problems like this. Okay, so that goes back to why do you need to choose a reference point? Well, again, because when you generate these torques, they have to be relative to some place. So what that means is I could choose this to be my center of the problem, or this to be my center of the problem, or this to be my center of the problem. You're still going to have angular momentum conservation around any of these points depending on where you choose them, but it will change this r vector depending on where you choose it. If that's not clear now, hopefully it'll be in a little bit. So in the interest of having the most symmetry possible, I'm going to choose this as my point of reference. So the center of this sprinkler system right here. That's a terrible dot, but you're going to have to go with me on it, okay? All right, so what else do we have? If we read the problem, in part A, we have a retarding torque. So that's simply just going to be over here. There's no other external torques on the system, so I think it's just going to be the retarding torque over here. And of course, since we have two outlets, we're going to have two integrals over our control surfaces. Okay, so what should we do to handle that? Okay, well first I'm going to write out what our expression is going to be. It's going to be this. So again, retarding torque on the left, and you're going to have two terms for the control volume over here. Okay, I'm going to move this so that we have some more space, because I'm going to start listing the vectors, because we've already done all the way up to 7 over here. So now what we have to do is we have to list these vectors, R1, V1, N1, R2, V2, N2, so that we could do the operations on them and simplify the problem. Okay, so first thing you should note is that we've chosen our center of symmetry, so our vectors, or our radius arms, need to be relative to that. So for here, if we're going to 1, well, I'll do 2 because it's a little bit easier. It's going to point right where like this. I wish they had these arrowheads, but I'll just do it like that. So first it'll point like that, and then since our outlet is right over here, the velocity stream will point like this. Cool. Okay, so how do we represent that in vector notation? Well, it's going to look like this. Not too complicated. So again, our R1 is simply, this is kind of, okay, let me switch these just so we don't get confused. Hold a sec. 1 will be over here, and 2 will be over here. Okay, that 1 got kind of cut up. Give me a sec. Okay, so this first vector, the radius arm, points from here to here, so that's directly R over, and then nothing in the vertical direction. And this flow is going, well, it's only going in the vertical direction. So it's simply going to have the magnitude V1 going up. And you probably already know by now that the dot product is going to be V1 because it's an outlet. Remember, our inlets are typically, the dot product turns out to be negative, the magnitude of the velocity, and the outlets turn out to be positive, the magnitude of the velocity. Okay, so how do we compute this cross product over here? Well, hopefully you remember, especially the simple 2D one, is that you could represent the cross product as the determinant of those two vectors. And again, this is why the order of the cross product matters. Make sure you always write R cross V. Don't write V cross R, because then all your torques will be generated with an extra negative sign. Remember, the cross product A cross B is not necessarily equal to B cross A. So you need to be careful with that. So that computes this, and that computes this. But wait, there's more. We have to worry about, well, let's slow down for a sec. How can we use symmetry to help us get our goal? Well, we chose a center of symmetry because if you do the R2 here and the V2 here, what you're actually going to get is something extremely similar to these guys and the outcome of these guys. You're actually going to get something that's, well, it's essentially identical because of the symmetry, because you could rotate this and still get the exact same thing on the other side. What that means is that you could simply double what you got, and that gets you this. So again, this V1R from the cross product is going here, the row is carrying over, this is from the dot product, and this 2 is because this entire part of the problem is entirely symmetric to this part of the problem. You could just reflect them over and it'll be the same thing. If the symmetry scares you, you could actually write out the vectors and do it, but you'll find out that, yeah, it's going to be symmetric to rotation, which is what you're looking for when you're doing these angular momentum problems. Okay, so what else do we need to worry about? Well, okay, remember when we were doing linear momentum, we like to write things in the form of rho VAV. The reason being VA is your Q, your volumetric flow, and then rho times Q is your mass flow. Well, I'm keeping it in that form, and then you have the radius arm hanging out over here. Okay, so the thing we need to be a little bit careful about is, what is this Q really going to be? And we have to be a little bit careful about that. So let's pull up the results from our continuity equation. So if you're doing the continuity equation, you're going to use the same assumptions here, and you know that you're going to get from a lot of the other problems, VA for the inlets will be the same as V out, A out at the outlets. So in other words, your volumetric flow is conserved throughout the system. Okay, but we need to be a little bit careful about this V out. How do we want to define this V out? So really there's two outlets. So I'm going to say V out, A out corresponds to one outlet. So that'll be the V out, A out here. And then to correct our equation, because remember, all the inlets need to be equal to all the outlets for the volumetric flow to be conserved, we need to add them together like this. So V1A1 plus V2A2 gets you the entire V out, A out. Okay, but again, because of the symmetry, V1A1 is actually going to be the same thing as V2A2. So what you have is this, where we've redefined our V out, A out to be just at one of these control surfaces. So what you need to remember is that over here, oh, okay, to keep the notation consistent, let me just put the 1 here, just so we don't get freaked out. 1, 1. So this needs to be adjusted so that it works with this equation. So what I mean by that is it's going to look like this. Okay, let's explain a little bit here. So remember, we're looking at this equation going to this equation. So what we're doing is we're taking this V1A1 and we're saying from this relationship it's really going to be Q over 2. The next thing we're doing is we're saying we have this extra V1, how about we use this expression, move the A1 and the 2 over, and we get this right over here. So we simply have 2 rho Q over 2, that's V1A1, and we have Q over 2A1, that's V1, and we have this R. And of course the A1 you could get in the standard way by just using the circular radius of the outlet. And the problem is essentially solved. Part A anyway. It's a little bit different when you're not dealing with retorting torque. So when we're not dealing with a retorting torque, how does that change the problem? Well, it means that you don't necessarily have this guy going on over here. So what is going on instead? Okay, we're asked to find the rotation rate. Okay, you have to remember back to your general physics. So let's simplify this guy over here. So when we had that expression on the left-hand side, originally, oh, well, it's gone now. When we had this, well, we can make the assumption that, okay, assume they're orthogonal, that gets you to this. Now if we take this differential operator right over here, what's going to happen? Well, let's go back a step actually. One of the most important things you can know how to do in fluid mechanics is dimensional analysis. So what do we know the units of this equation have to be? Well, let's just go through each of these terms and say what the units are. Rho is going to be some kilograms per meter cubed. Volumetric flow is going to be in meters cubed per time. Here we have meters cubed per time again, but we have this area in the bottom, and here we have this R that's just going to be in meters. Okay, so we know that on the right-hand side we're going to have kilogram meters squared per second squared. What are the units here? Kilogram meters squared per second. So we're missing an element of time, and that's where this guy comes in. If you take the derivative of this, well, what's going to be varying? Is the velocity of the fluid going to be varying? Well, no, we assume the velocity profile was constant. Is the radius arm going to be varying? No, that looks like it's not going to change. I mean, it's just the pipe. So the only thing that can change is, well, it's going to be the mass flow rate. So you're going to have a flow of mass per time coming out. So what that's going to look like is this. So again, what is rho q? Rho q is really m. Okay, what's going on here? Well, you have to remember from general physics that V equals R omega. So we make the substitution that this m is really a flow rate, and it's going to rho q. Sometimes you'll see an m dot for mass flow rate. And here we have this d dt. I'll say approximately. Well, you have to remember that this v is going to be r omega, so we get this r squared omega because we're at the point of the control surface. That's the point we're looking at for the rate of rotation. Okay, and then we simply have whatever we had before. So all we've done is we've changed this torque term over here to this expression. Then we can do a bunch of cancellations, and what we're going to get as a final expression is going to be, you're going to cancel a bunch of things out, and you're going to get this. Okay, so note that you have Q over 2AR, and you have two outlets. Okay, you're probably still a little iffy on this problem. I could have probably explained some things a little bit better. So let's actually do another very similar problem. Okay, so this time we have flow coming out through here, and it's going out to 3 different spots. So let's go through our method. First, identify the control volume. That's going to be everything. Next thing you want to do, identify the control surfaces. Bam, 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 just like that. So we have 3 control surfaces. Okay, do we have any external torques? Well, what does it say here? Okay, if collar friction is negligible, so there's no collar friction going on, what's the steady rotation rate for this and this? So that sounds like we have no retarding torque this time. So, retarding torque this time. So we're going to be pretty much dealing with part B of the last problem. Okay, so what else can we do? We could use symmetry to simplify our problem. So again, everything is symmetric to rotation, so how about we turn it so that it looks like this? This will make our vectors a lot easier to write. And we know that this guy and this guy are going to be symmetric to this guy, so we're just going to look around at this guy and pretty much make everything in regards to him. And in that respect, we should make this right here our point of reference in regards to our torques, because that point is the point of symmetry. Okay, so from our same assumptions, this is going to be our starting equation for this problem. Remember, this 3 is because all 3 of these are symmetric, and these just come from making beta equal to angular momentum for our Reynolds transport theorem. Okay, good so far? Hopefully good so far. Okay, let's see what our continuity equation gets us this time. So remember, our V in A in must equal our V out A out, because the volumetric flow rates must be conserved. But remember, this time we have 3 outlets. So we need to group them all together. Oh wait, they're all equal, so we could just say the volumetric flow rate is equal to 3 times whatever the velocity and area is at that outlet. Okay, now we're ready to start writing the vectors. And we're only going to write the vectors for here because, again, the symmetry makes us ignore this and this. So our radius arm isn't too difficult because it's just going to point outward. So that's this over here. Let me color code these. For green, remember this is just going straight to the right. This big R should actually be this little d. Don't get too confused about that. This n out is going to be, well, the dot product with this will just give you the magnitude of the velocity. But over here, remember that this angle, the sine will give you the horizontal component, the cosine will give you the vertical component, and it's going up and right, so both of them are going to be positive. So now that we have those, we just simply throw that straight into our vector equation, and our dot and cross product will come out to be this. So this time, our R out, V out. Well, remember when you're evaluating these determinants, first you go diagonally like this. That'll get us 0. And then you add that to this. But remember when you're going back this way, this is going to be negative, and this is going to be positive. So you get R V cos theta, and you get a negative sign coming out in front. I'm going to assume you remember most of your vector calculus. If not, just brush up on it a bit. It's not too bad. Okay, and we're going to throw that directly into our transport theorem. And once again, we're going to get this. So everything on the right you should understand. The cross product just came from the vectors we did. That's over here. This V from the dot product of the outlet is going to be positive, and this 3 comes from the symmetry. And everything's going to be constant. We're going to be able to pull everything out and just integrate over dA. Over here, you might still be a little bit confused. Remember, we had no retarding torque this time, so we're interested in the angular velocity that we're going to have at that point. And we have this mass flow and this VR, and the reason for that is really because of that time derivative on the left-hand side when you're deriving this expression over here. But you could just remember the dimensional analysis we went through, that this has to be kilogram meters squared per second squared. And so this gets you a 1 over second, and then this gets you a 1 over second. So this gets you m dot VR. And the units over here work out with the units over here. Okay. So then again, we need to be a little bit careful, but it's going to evaluate to this. So again, we have that form rho VAV, and we just have this R term over here. We have this coefficient out here for the symmetry. And over here, we used V equals R omega to get this R squared omega over here. Okay, so one thing that should be emphasized is this over here. And I should point it out again over here. Remember when we were getting this over here, when we turned this V1A1 into Q over 2. And the reason we needed to do that was from our continuity equation, we knew that each outlet would have half the total flow. Okay, but over here, when you're doing the mass flow, m dot, or mass per time, you get the total rho times Q, because the mass that's flowing out is everything that's going out through this pipe system. So this outlet and this outlet. And in this problem, that's going to be the flow going out through all 3 of these. So that's this, this, and this. So you just get rho Q, not rho Q divided by 3 or any combination of rho Q 2/3. It's going to be the entire flow going out. But over here, with this VA term, just like before, because of our continuity equation, when we make the substitution, our V out, A out is actually just going to be Q over 3. Don't forget this, because this is how most people mess up the final problem. So we make that substitution over here, and this is what we get. And the last thing we do is a bunch of cancellations, and that's just going to get us this. And remember, this V goes to Q over 3A, because these 3's cancel out. Look at how similar this expression is to this expression over here. If you have 2 outlets, your final expression for the angular velocity is going to be Q over 2AR. If you have 3 outlets, it's going to be Q over 3AR. This cosine theta just comes from this bent in the pipe here. Over here, what do you think the cosine theta was? Well, I'll let you think about it for a bit, and it should be decently obvious. Okay, so let's do one last problem. This one will be a little bit different. So here we have water flowing through this pipe and coming out through here. This time they actually chose our point of reference, and they said, hey, your point of reference is right here at B. So we're forced to use that. It's not too bad because there isn't really any good center of symmetry. Well, I guess you could use here and then rotate it. But They don't want us to do that, so let's do the problem from the perspective of B. Okay, so control volume, everything in the system. Our control surfaces are going to be here and here. And the problem this time is that these control surfaces are not rotationally symmetric to our point of reference. So we're actually going to have to do work at both those points. So our starting transport equation is going to look like this, where again we have the sum of the torques on the left, and now we have two control surface terms because we couldn't use symmetry to simplify everything. Okay, so here again we're going to need to list our vectors. And remember, they need to be from B. So from here to here, we're going to call this distance R1. And remember, that needs to be left or negative because we're going from B to wherever the velocity is. So that's going to be negative R1, 0. And of course, the velocity is going in, and the normal vector is pointing out, because remember the dot product of the inlet is typically negative the magnitude of the velocity. But wait, what do you notice is going on here that's even better? What do you think, just from either looking at the geometry of the problem or from seeing these guys over here, what do you think is going to happen? Well, what's the cross product here? If you imagine this as your bracketed determinant, you're going to have R1 times 0, that's 0, and then V1 times 0, that's 0. Your cross product is going to be 0. So this term is completely going to cancel out. And again, that's pretty clear from the geometry here. How could a flow going collinear with the velocity being collinear with the moment arm, how could that possibly generate a torque? And it can't, so that's why this term disappears. Okay, let's write our vectors for the second point. Okay, so let's call this L, and let's call this distance along here, let's call it R2. So in the x direction, this first goes along the vector, well, it goes along L. It had to take this cosine 50 because we're taking it up to the horizontal, and it's going an additional R2 this way. So this is L cosine 50, and this is R2. And then over here, it's going L sine 50 downwards. So that's going to be 0.9. So you don't get confused and say that L equals 0.9. I'm just going to write it in over here that this is entire thing, L sine 50 is 0.9 meters. And of course the velocity is just going straight out in V2, and the dot product is going to just simply be V2. So now let's compute those operations over here in our vector equation, and this is what we're going to get. This expression over here, you could do the math here if you want. It's not so important. And one other thing we need to worry about is that we actually have to identify the torques in the system. We're told that there's a pressure P1 over here. So P1 at the inlet and P2 at the outlet, and they're not gauged. So we have to worry about these pressures exerting torques on the system. Okay. But you have to remember, when you're having forces exerting torques on the system, that's going to follow the form of R cross F, because that's what torque equals. Well, the moment arm for this torque due to pressure 1 is going to be collinear with the direction of the force that results from this pressure. So we're going to have nothing that comes from P1, but we're going to have a term that comes from P2, because we're going to have essentially the same moment arm that we have for the velocity. So that external torque equation on the left is going to look like this. We have that P1A1, this will cancel out, as I just said before. This, we don't know yet. We could write the vectors for that. This should be a vector for the P2. And we have this stuff over here resulting from what we just did. Okay, we could simplify that to be this. as I said 3 seconds ago. And okay, where does this come from? Well, it just comes from, if you're going to write out the vectors, this is going to be your cross product, and it's going to give you that. It's going to be pretty similar to what we did over here. If you're really interested in looking at the math, just pause the video and you could work out how I made that expression. Okay, then simply, just as before, this time we're solving for the torque at B that keeps the system together. So we're just going to simplify this expression in terms of the torque of B. And again, what do you see over here? You have this Q coming. Where's that Q coming from? Well, here, everything's flowing in and everything's flowing out. So we have just one outlet. We don't have any of that symmetry to deal with, so we have the entire Q over here. This Q over A2 from the continuity equation is just going to be this velocity over here. So this goes to, these both go to this, and over here, L sine 50, remember that's just this 0.9 you see along here. It's not 0.9 sine 50, it's just 0.9. And over here, well, that just came from the previous step where we did the cross product. So I know that was a little bit confusing, but I hope I at least demonstrated through the math that as long as you break the problem into smaller components, think rationally, use symmetry, and write the vectors, then you'll be able to solve any of these problems.